Light allows us to view everything, from the very large to the very small. But what exactly is it? Scientists have been asking this question for centuries, and through a series of groundbreaking experiments have come just a little bit closer to understanding the gravity of its remarkable properties. One of the first influential theories about light's composition was developed in 1678 by Christian Huygens. Huygens developed on other Italian physicists' research and theorized that the diffraction and refraction of light could only stem from wave-like properties. At around the same time with the conflicting view, Sir Isaac Newton, in his publication Optics, theorized that light was a massless, perfectly elastic particle, with colors being a result of size variations. Wait, so which is it? A wave or particle? Well, it's kind of both. Throughout the next century, a series of experiments proved that light did not only contain wave-like properties, but also was part of the electromagnetic spectrum. This notion would be challenged in 1801 by what we now call the double-slit experiment. In this experiment, light was shown onto a surface while passing through a single slit or a double slit. When passed through the single slit, light acts as one would expect particles to act. A large concentration of the light landed directly behind the opening onto the surface. This is similar to paintballs being shot through a single slit, as most would land directly behind the opening. But when shown in front of the double slits, the light landed not as two concentrations, but as several evenly spaced concentrations with little space between them. This is how one would expect a wave to behave because of wave dissipation, and this bewildered scientists. How can light behave as a particle in one instance and a wave in another? Introducing the photon. In the late 19th century, when experimenting with the unique properties of light, physicist Heinrich Rudolf Hertz noticed that only certain wavelengths of light were able to eject electrons from a metallic surface. This was later dubbed the photoelectric effect. This was contradictory, as it was believed that all wavelengths of light were able to agitate any metallic surface enough to eventually eject electrons. When explaining the reason for the photoelectric effect, Albert Einstein theorized that light traveled in wave packets, or wave-like formations traveling in units, and exhibited both wave-associated properties such as dispersion and particle-associated properties such as probabilistic uncertainty. This concept was later named the photon by Gilbert Lewis. What does this mean, and why should you even care? The discovery of wave-particle duality has profound implications in our understanding of subatomic particles. Matter, at the smallest level, provides clues for us to understand a vast universe we are yet to explore. Various theories have since evolved in physics and owe their origin to wave-particle duality, and some of these theories even pose direct challenges to the way we understand the world around us. Welcome to the world of quantum mechanics.